So problem number 6 looks like this. Y equals x minus 3 over x. Let's first start by figuring out the domain here. What value of x can't we use in this one? 0. So it's kind of like everything but 0. So that's our domain. It's everything but 0. Or I could write negative infinity to 0, union 0 to infinity. Probably easier to write the former rather than the latter. Just looking at this function, can anyone tell me one of its features? All right. Top and bottom, they have the same degree here. So what's that mean in terms of... Perfect. So because the degree of the numerator and the denominator are the same, the limit as x approaches infinity or negative infinity of x minus 3 over x will be 1. Therefore, right, the triple dots, y equals 1 is a horizontal asymptote. So that's a big feature of our graph. What's another feature that you can kind of just look at it and say, okay, I can see that this is going to happen? Anything?
Y-Intercept is 3.
All right, the X-Intercept is 3. That's good where the numerator is equal to 0. So let's keep track of that. X is 3, Y is 0. That's our X-Intercept. Good. Is there anything else that you can just kind of see based on the graph? Or based on the form of the equation? All right, good. There's a vertical asymptote, right? Where's the vertical asymptote? X equals 0. Where the denominator equals 0, you're going to have a vertical asymptote. So x equals 0 is a vertical asymptote. Nice. So our graph is coming together pretty nicely. Let's actually get down to the business of some calculus here. You're not going to escape any of these problems without doing at least a little bit of calculus. You're going to want to see some. Where's that going to take place? Well, let's find some derivatives. Now, as it stands, I have to use a quotient rule. But I encourage you, when it's convenient, to try and avoid the quotient rule. Is there a way I can avoid the quotient rule for problem number 6 here? Perfect. Let's rewrite this as 1 minus 3 over x. So you're dividing both terms by the term in the denominator. In fact, let's go one more. How about if we write that as 1 minus 3x to the negative first power? And then it'll be really easy to find the derivative here. In fact, go ahead. Try and find first y prime and then y. So how about first y prime and then y double prime? That might make a little bit more sense. We will at some point kind of go backwards. We'll start out with y prime and then look for y. That'll be the last thing we cover in this course. It is kind of cool. All right, so some takers. What's y prime going to look like? 3x to the negative 2. Good. Someone else, who want to hear from tonight? Someone for y double prime. Someone else, maybe in the back, wearing glasses. Good. Negative 6x to negative 3. Now I want to know where this function is increasing and decreasing, what its concavity is. So I need to know where this can change signs. So that's 3 over x squared, and this is 6 over x cubed. It can only change signs where either the numerator or denominator equals 0. Let's start with the derivative, the first derivative. Negative 6, thank you. So x, y, and y prime. Where's the one place where the denominator could change sign? Could change sign. It doesn't necessarily have to change sign. Where could the derivative change sign? Well, the numerator is always positive, right? The denominator could change sign at 0, although really it doesn't. But we still have to take a look at the function on either side of 0, on either side of our vertical asymptote. And we can test points here. What would be some good test points for us in this particular case? Yeah, -1 and 1. Those work as good test points. If you plug them into your derivative, what's the sign of the derivative going to be at -1? It's going to be positive. Yeah, you're going to get 3. So that represents that it's increasing. And to the right here, it's still positive. So it's still increasing, right? It's increasing on both sides. We'll have to figure out what that means. Let's take a look at the second derivative. So for the second derivative, I have a similar case to the first derivative, in as much as at 0, that's the only place where the second derivative can change signs. The second derivative, this backwards e here is some mathematics script. Backwards e means there exist. There exist. If I do this, backwards e, and then we'll do a slash through it, what am I trying to say? Doesn't exist, yeah. The second derivative doesn't exist there, right? It's undefined at 0. That's okay. We can look at the second derivative to the left of 0 and to the right of 0 and see what happens. So to the left of 0, if I plug in a point, say, I don't know, let me be adventurous and use, I don't know, -1. All right. If I plug in a -1 into my second derivative, it's going to be positive. But let's be careful. Positive second derivative does not mean increasing. What's a positive second derivative mean for us? Concave up. All right, so concave up. And then, continuing to be super adventurous, let's go to the right and test x = 1. I get negative. And what's that telling me? Concave down. Good. Let's put all this together in the form of a graph. So, like I said, if you want to borrow rulers, I've got them up here. One, two, three, four. Don't think I needed those, but that's all right. Let's start by drawing our asymptotes. Those are the most important features of our graph. And in fact, I think for my graph, let's let this be a 1 here, -1, etc. So that I'm using a little bit bigger scale on the y-axis than I will on the x-axis. On the x-axis, I'm just going to use a regular scale of 1 unit per tick mark. So the big feature that we have to include first is the horizontal asymptote, and that's at y = 1. I'm going to do that with a dashed line because this is really not part of the graph, but it does somewhat frame our graph. We also have a vertical asymptote at x = 0. X = 0 is also known as the y-axis. We've got an X-Intercept at 3, so the graph is going to come here, pass through the X-Intercept. And then other than that, what else do we know? Well, we know that it's increasing to the left of 0 and to the right of 0. We know that it's concave up here and concave down here. Here's my best guess as to what this looks like. And of course, you can and should check this on your graphing calculators. I'm not going to take away your graphing calculator on the exam. So when you hand things in, make sure that your graph at least matches what you have in your graphing calculator. I'm thinking it's going to look concave up here, concave down here, something like this. Now, I'm not really taking care to plot points. That's okay. If I wanted to plot a bunch of points, I'd ask you just to do that on your calculator. What I am getting is the nice big picture, increasing, increasing, concave up, concave down, vertical asymptote, horizontal asymptote, and X-Intercept.
Will you want to see points plotted?
Not really.
Or do you just
No.
want
The only points that I would want plotted are X and Y intercepts and critical points. Those are the points that I'm going to want to see plotted.
Is that where, like, you should start the graph, like the X and Y intercepts? Is that where you think you should start the graph?
I think you should start with the horizontal and vertical asymptotes, if there are any.
Like after that?
Yeah, those points, sure. But you know this is a vertical asymptote, so one of two things is going to happen on either side. Either it's going to go up towards positive infinity or down towards negative infinity. In this case, it went up towards positive infinity. Over here, it goes down towards negative infinity. Of course, that's just my guess. I should probably double check that. I don't know. Did anyone double check it? Is it more or less look right the right thing? All right. Thank you. No, to check this, to check that I got the graph right, it actually go back and plug in the function itself. That's what you plug in. That's a great question because a lot of people, they accidentally use the wrong function at the wrong time. They're graphing the second derivative when they mean to graph the function, or they're testing the first derivative when they should be testing the second derivative. So it's a good question. It's something you want to take care of is, well, which function should I have in my calculator at any one time? Anything else on number 6 here? Okay. Let's try one more here. Then I'll pause and save the video, and then I'll give you a little humor break as well. I haven't written the exam yet. So
I know there will be one, obviously, but like
yeah, yeah, I don't know. I haven't even thought about the exam yet. That's like, God, that's not till like Monday night, right? Let me tell you now that I'll probably test you on several parts of all these different things, but I try and be reasonable. I mean, you look at the last exam, and for those nasty problems where you had to do the related rate stuff, I said choose 2 out of 4. Now, I'm not sure what you think, but from my perspective, I think that's pretty generous. I think that's giving you a lot of flexibility. And I don't think I'm really going to change, even if my favorite hockey team loses this Saturday night. Even though the Spartans own us in basketball this year, I'm still going to be writing a reasonable exam.
because if there's going to be like multiple ones, do you want us to get really good at doing them like time-wise, like be able to do them quickly?
Look, I haven't written it yet. I haven't even thought that. Let's just get through this stuff, okay? Okay, let's look at, let's see, problem number 12. Let's see, should we do 12 or 20? Didn't we do one that was almost like 20 in section 4.4? Or didn't we do almost like the exact one? Yeah, we did this exact one, right? Yeah. Yeah, we did 12. So, all right. So let's do problem number 20. It's kind of a friendly one. Y equals x minus 1 to the 5th. Now, one thing you can be happy about is I'm not going to ask you to expand this. I'm not going to ask you to write it all out. Instead, let's just recognize that it's a polynomial. So what's that mean about its domain? All reals. So negative infinity to infinity. Let's try and pick up a couple other easy things about this. It's not going to have any symmetry that we're going to be able to use very easily. So let's try and find, is there going to be any asymptotes? Well, it doesn't have a denominator, so it's not going to have a vertical asymptote. It's not going to have a horizontal asymptote, so no asymptotes. Okay, no asymptotes, no symmetry. Let's try and find some other easy points. Let's try and find the Y-intercept. How do you find the Y-intercept? Good. If you set x equal to 0, what do you get for y? Negative 1. Let's find the X-intercept. To find the X-intercept, you set y equal to 0. And if you have 0 equals x minus 1 to the 5th, well, what could I put in for x to make this equal to 0? 1. So we got a couple easy points right there. We've got an X-intercept at 1 and 0. We've got a Y-intercept at 0, negative 1. Okay. Let's start working with derivatives. As far as the first derivative is concerned, y prime is going to be 5 times x minus 1 to the 4th. That's the derivative of the outside times the derivative of the inside. Yeah, unfortunately for us, the derivative of the inside is 1. So how about y double prime? Yeah, 20x minus 1 to the 3rd power. So you're using the chain rule, or the power rule and the chain rule. So 4 times 5 is 20. Subtract 1 from the exponent times the derivative of the inside, but the derivative of this inside again is 1. Let's set up a couple tables here and evaluate the first and second derivatives to see what that tells us about the function. So x, y, and y prime. Let's choose a couple points to plug into and evaluate our first derivative. I need something to the left of 0 and something to the left of 1 and to the right of 1. So 0 and 2 probably present themselves pretty quickly. Do I need to pull out my graphing calculator on this one? No. You've got something to an even power. So when you raise something to an even power, what's the sign of that going to be here? Positive. It's positive for both cases, for 0 and for 2. So Lawrence, this is positive both here and here. What's that tell me about y? What's happening there? Good, it's increasing. So increasing and increasing. Good. Let's work on the second derivative. So second derivative, x, y, y double prime. Same game. X equal 1 is where it's all happening. And we want to test on either side. We can use the same points as before. That's not cheating. 0 and 2. What are the signs this time? Good. Negative and positive. Nice. So, good. Concave down, concave up. All right. That's pretty much as we're going to get out of this. There's no more magic we're going to be able to find. So in terms of graphing it, we have a function which is always increasing. So it's increasing from negative infinity to 1 and from 1 to infinity. And then it's concave up from 1 to infinity and concave down from negative infinity to 1. So your graph should match all of that information. What happens is that near x equal 1, this graph is going to be really, really flat. Yes, sir? That's where this could change signs. You solve where this is equal to 0. So where does the first derivative equal 0? Well, when x equals 1. Where does the second derivative equal 0? At x equal 1. And when those are equal to 0, on either side of it, it could change signs. So it could be positive, it could be negative, and that's where we test points to figure things out. Yeah, it happens to be the X-Intercept in this case. Yeah, in this case, but it's not always going to be the X-Intercept. So last but not least, let's draw the graph. You're going to have a concave down shape coming into the root, and then leaving the root, or leaving the X-Intercept, you're going to have a concave up shape. The graph is probably a little bit flatter than what I've drawn here, but that's okay. I'm not looking for pinpoint precision. I'm looking for big pictures. I'm looking for your graph to be concave down here, concave up here. And notice that it's increasing everywhere. It's just the way it does it changes a little bit from to the left to the right of x equal 1.
I think it's better to pay more attention to the
Concavity?
concavity when you start drawing, then it'll take care of the increasing, decreasing, I think.
Not necessarily, because
Well, it was increasing for both, but if one was concave down, the other one was concave up.
a function like this is concave down until you get to 0, but here it's decreasing even though it's still concave down. So concavity doesn't necessarily match where it's increasing or decreasing. It's okay. You're not alone. You're not alone.